welcome everyone. Alright, so finally we made it through voltage drop, at least hopefully you mostly understand that, since that is our most used test. Of course, we have a lot of other tests that we use as well. One of those being checking resistance or measuring ohms. You could say that traditionally we've really only done diagnostics by measuring available voltage and by measuring resistance. But now, of course, we use mostly voltage drop. That doesn't mean that there isn't a place for measuring resistance and amperage. There are many circumstances where it's actually better to measure resistance, especially if you're just trying to measure a component, all right, just by itself. So today, that's what we're going to be talking about. All right, so I'm going to have to teach you the how and the why of resistance and amperage before we can actually take our meter and start poking and prodding all over the vehicle and take measurements. We definitely need to understand what those measurements mean, how to decipher them, and ultimately how that can help us fix a vehicle. All right? So right now we're going to take a look at a basic circuit. Same thing that we have done before for voltage drop. So we all know now that electrons, and really we are talking a lot about electrons today because we are talking about amps and resistance, or electron flow and the resistance of flow for those electrons to get from one place to another. Okay, so we simply start out with the battery. We know that this is our voltage source. It's also our source of amperage. So this is essentially where all of those electrons habitate or live. Okay? So we have a positive post and we have a negative post. Electrons technically flow out of the positive side, come down, erase that right here. Okay, and the electrons have to flow through a circuit protection device. This circuit protection device, normally on most of our cars that we work on, are going to be fuses. This will help protect the circuit in case these electrons flow too fast. All right, if the electrons flow too fast, then we run into a situation where the wires can burn, melt, and potentially create a fire hazard. Okay, we're not just talking about an inoperable circuit, but we're talking about something that's very potentially dangerous. Okay, so our fuse symbol is, again, sort of like an S shape. So those electrons go through the fuse, and a switch can be located anywhere in the circuit, but in this diagram, we're just going to say that the switch is on the other side of the load. Okay? So again, we're going to use our light bulb example. All right. So electrons are going to flow from the battery through the fuse and over to our bulb. All right. We understand that. Now, of course, we need a path to ground in order to convince those electrons to come out of the battery. As long as they know they can get back to the battery, they will flow. Okay? So the electrons go to the bulb, light the bulb up, come back around, go through whatever switch we have installed. Okay, normally, in this case, we're going to talk about headlights again. It's going to be a headlight switch. Okay. And then it just goes right back to the battery on the ground side of the battery. And then they can start their journey again from the battery around to the light bulb, back through the switch, and over into the battery. Now notice that I drew my switch normally open because that's normally how we see them in diagrams. But you have to be able to visualize on occasion that once you have actually activated the switch, that it will no longer be open, that it is actually closed. Okay, so hopefully everyone is on board with that. Okay, so hopefully everyone now understands how current flows. From the battery, they go through the fuse, they follow their nice little road that has been laid out for them, activate the bulb. Okay, they do the majority of their work here, go back through the switch, and back to the battery. And then they will start that cycle all over again. Okay? because that is, by definition, what an electrical circuit is. All right. Now, these electrons, as I had said before, can sometimes be dangerous. If they're able to freely flow through the circuit without any work to perform, such as if this light bulb did not exist, in this instance there's so many electrons, okay? As you can see here, right now we just have, let's call it one column or one row of electrons. But if there's no work to be performed, if there's no resistance, then many more electrons will try to go from the positive side of the battery over to the negative. Okay, and this is overload. These small wires cannot handle all of these electrons going through it at any one point in time. So what we have to have is we have to have that load. We have to have that resistance inside of the circuit. Okay, let's put our bulb back in there. We really need our bulb, all right, so that our fuse doesn't blow. All right, because when we have all of those electrons flowing through the circuit at one point in time, then our fuse, the metal inside that fuse, will heat up to a very high temperature and it will pop. It will blow the fuse, all right? And that will keep any electrons from going through the circuit because they know they can get out of the battery but they can't get back, so they just stay inside of the battery, all right? So now that we have our bulb back, now there's work to be performed. So the electrons are not going to be able to get back to the battery as quickly, and not as many of them will leave the battery. All right? Only a few will volunteer to go and perform the work of lighting up this bulb. Okay? So now you have far less electrons traveling through the circuit. An amount of electrons that the circuit can handle, this amount of electrons or this amount of amperage will not blow the fuse. You'll notice that every fuse has a rating. So for instance, this fuse might be rated, considering it is a headlight bulb, it might be rated somewhere around, let's say, 15 amps. Sorry, it's a little hard for me to draw with my finger, but so this will allow only 15 amps through that fuse. If we go over 15 amps, then that fuse is supposed to melt and pop. Now obviously if a circuit has a 15 amp fuse, then the circuit will not actually have 15 amps flowing through it at any one point in time, because if that was the case, then any small additional amount of amperage or small additional amount of electrons flowing through that circuit would cause that fuse to blow. So normally, if you have a circuit that is rated for 10 amps, you'll put a 15 amp fuse in there. Okay, so now let's talk about Ohm's law and how this all comes together. All right. So as you may have already figured out, the more resistance we have, or the more work that has to be performed, for example, the work that the electrons need to perform in order to light this bulb, the less amount of electrons that you will have. So the amount of work that needs to be performed, we can measure that in something that we call ohms. Ohms is basically a measurement that we use to calculate what the resistance of current flow actually is. For example, this bulb was rated at 3 ohms. Okay. Now, there is a certain amount of amperage in the battery, but sometimes you can't actually use the amperage of the battery to calculate how much amperage is actually going to flow through the circuit. It is dependent upon how much voltage you have in the battery, which we all know normally it should be 12.6, but just for mathematical ease, we'll use 12 volts. Okay. So we have 12 volts here. All right. So if we have a certain amount of pressure, we can push a certain amount of electrons through a circuit. Now, the less resistance there is, the more electrons we can convince or pressure to get out of the battery. the more work that has to be done, well, you're only going to have a few people or a few electrons that would volunteer to get out of the battery to perform that amount of work before they come back home. Okay, so if we have 3 ohms and 12 volts, we can do a simple, very simple calculation to figure out how many amps should be flowing through this circuit at any one point in time. Okay, so our calculation goes like this. 12 volts divided by, take a guess, 3 ohms, right? Okay. Equals 4 amps. Okay? So there's really not a whole lot to Ohm's law. It's really very basic, and this is for the most part all it really is. But as you might imagine, we can also calculate how much resistance should be in a circuit by using the same law. Okay? We know that we should have 12 volts, and remember, always check your battery, always check your fuses before doing any sort of diagnostics. Okay? So we know that we have 12 volts, and let's say we actually just went ahead and measured amperage in the circuit. And we know that we have 4 amps going through the circuit at any one point in time. We would use the same calculation. Okay. 12 volts divided by 4 amps would give us 3 ohms. Okay? So there's no reason to be afraid of Ohm's law. It's a pretty simple law, and although we do a lot of calculations in this class, it's really just to help you fully understand the relationship between resistance and amperage. Okay, so now we're ready to start taking some actual measurements on a vehicle that is operating normally. And of course we're going to use our low beam headlight again in this example, and we'll also hopefully add in a few things about voltage drop just to help you understand that a little bit better as well, which this will help you do for sure. Okay, so before you can take a measurement, you have to know how to set up your meter in order to do so. All right, so right now my meter is set to off. Obviously you can't measure much with that. Okay, and just like we did with voltage drop, we're going to hook up our jacks the same way. So obviously our black lead goes into the common jack, which is also for ground. And our red lead will go into the volt ohm jack, okay? And we're going to start off with ohms. So since we're going to start off measuring just ohms, we will turn our meter to ohms, and it's just this little horseshoe symbol up top. All right? Now whenever you do turn your meter to ohms, it's always good to touch your test leads together just to make sure that your meter is functioning the way it should. So we should have very little resistance, or hopefully 0 ohms when we have our 2 leads connected together, because obviously between the 2 leads we don't have a light bulb or any sort of resistance. Okay, the only resistance we're getting is between the 2 actual leads itself, which is very little. Okay, 2 to 1/10 of an ohm is negligible. It's almost nothing. Okay. Okay, and hopefully you've also noticed that when the meter leads are not touching, you get this OL reading on the screen. That stands for over limit or open loop, which we know that a complete circuit is a closed loop. Okay, when a switch is closed, we've closed that circle and the electrons are able to flow. Open loop is that circle is disconnected in some way, shape, or form. Okay, open loop also and OL can also mean infinite resistance. So, but for the most part, OL means over the limit. So it is more resistance than this meter can actually read. Certainly we have an open loop because our meter leads are not touching at all. So if I touch my meter leads together, that's a closed loop. Meter leads apart, open loop. All right. Now we're almost ready to begin measuring on the car. But please remember that when you are measuring resistance, you have to disconnect the component from the rest of the circuit. So we're not measuring it live and in real time like we would with voltage drop or even with amperage. Off and disconnected, and then it will be safe for us to actually measure resistance with our meter. Otherwise, you can actually blow your meter if you have the circuit on and connected. Okay, so one of the first measurements that we're going to take on the vehicle as far as resistance is concerned is measuring resistance of an actual fuse. We know that a blown fuse is a very common cause of an inoperative circuit. So we have to make sure that we check fuses. Normally we don't do it with a meter. Normally we just use a test light, and that's mostly fairly accurate. But there may be some instances where you might want to actually ohm check or measure the resistance of a fuse if you think that it may have some high internal resistance, or you get one of those strange fuses that actually do light up on both sides, but it's actually broken outside of the standard fuse terminals. Okay, so here I have a sample fuse for you. Now I'm just going to show you right now. We know that this fuse is already blown. So think for a moment to yourself, what sort of meter reading would you expect if you have a blown fuse? Okay, so we're going to take our 2 meter leads and measure on both sides of this component. In this case, one side of the component is this blade of the fuse, and the other side of the component is this blade. So let's begin. Okay, so to measure this fuse, I'm going to take 1 meter lead, place it on one side of the fuse, and the other meter lead and place it on the other side. And you can see that although I have full contact on this fuse, that we have an open circuit. So this is open loop. Now let's try to do the same thing with a good fuse. Okay, for the good fuse, I'm going to use fuse number 65, which is the fuse for the left-hand low beam headlight that we are theoretically testing. Okay, and again, I'll just place that down on top of some plastic. If you measure the fuse in your hand, the meter can actually send electricity through your hand to the other meter lead, and you'll get a high resistance reading. Okay, so like right now, I myself have a resistance of 2.1 mega ohms. Obviously I'm not a great conductor, but just don't want you to be fooled during testing if you do that. Okay, so I'm going to again just touch 1 meter lead to one side and the other meter lead to the other side, and we get a reading of 0.2 of an ohm, so less than 1 ohm, significantly less. And if you think about how when we touched our meter leads together, we got pretty much the same reading, this fuse has very little, if no, resistance in it. So it wouldn't use up any voltage if we were to do a voltage drop on it while it was actually live and inside the fuse box. And it is able to allow current to flow through the fuse and to the rest of the circuit. Okay, so now we're going to measure the resistance of another component. This is the actual component that is, by the customer's concern, malfunctioning or not working. So the way that we would test this headlight bulb is first disconnect it from the rest of the circuit. Okay, we don't want the circuit on or active or anything like that. We just want the meter to do all the work. So you can take this headlight bulb out, and you can see that it has 2 filaments inside of it. One is for the high beam and one is for the low beam. And we'll go ahead and check both. So before we measure our actual headlight filament resistance, we want to make sure that we're measuring the correct filament. In this instance, we really want to focus on the low beam, but it's also good to compare and contrast what the low beam resistance is versus the high beam resistance. And this will give you a better idea of why high beam is so much brighter than the low beam. All right, so Okay, so we have on the headlight bulb itself, pin number 1 is going to go to the low beam headlight, just as we had discovered in the previous video. And of course, every circuit needs a power source, but it also needs a path back to ground. So we're going to place our meter leads on pin number 1 of the actual headlight bulb and pin number 2 of the headlight bulb. Okay, so if you have trouble orienting yourself to which pin on this headlight bulb belongs to the low beam, which one is pin number 1? Is it on this side or is it on this side? We can always take a look at our wire colors. So for instance, we have this tan and white wire here that goes to the low beam filament. So we know that pin number 1 is on this corner. And of course pin number 2 will be in the center. That's our black wire, that's our ground. So we have power that goes through the low beam filament, comes back out to ground, goes back to the battery. Right. So let's take a measurement. We have our meter all set up, and first we're going to measure resistance of the low beam filament, which will be done by placing our meter leads at terminal number 1 here on the bottom end, and the center terminal, terminal number 2. So I'll just go ahead and show you guys what that looks like here. Okay, terminal 1 and terminal 2. Okay, oh, sorry, let me do that again. Terminal 1, terminal 2. And our high beam filament will be measured by measuring terminal 3 and terminal 2. Okay, so I'm just going to place this back in the headlight. So it can hold it for me, essentially, is what I'm going after. Okay, so let's go ahead and measure our low beam filament. Alright, it's sometimes a little difficult to ensure good contact on your terminals. Okay, so here we have 4/10 of an ohm. Not very much, especially since the bulb is not lit yet and it hasn't started to develop any sort of heat, and therefore the resistance is not increasing. And now let's go ahead and measure our high beam. Alright, now our high beam is really only giving us 3/10. So we have less resistance on our high beam circuit than on our low beam circuit. So now we know that our high beam filament has a little bit less resistance than our low beam filament. And we know that less resistance equals more amperage, or more electron flow. Alright, so how do we measure amperage? Now normally we're going to measure amperage by disconnecting the circuit and allowing our meter to become a part of the circuit. And so all of those electrons and all the amperage will flow through the meter, through the bulb, and back to the battery. But unfortunately, that can come with its own set of issues. If you're flowing too much amperage through this meter, you can damage your meter. Okay, it's very easy to blow a fuse in a meter and actually bypass the fuse and unfortunately destroy the meter itself, and then you're out a couple $100. So let's not do that, all right? Instead, I like to use what's called an inductive pickup, okay? Now the way it works is pretty magical, all right? All that we're looking at is the magnetism around the wire that's created by the electrons passing through it is measured by this. And that magnetic field is actually a form of pressure or a form of voltage. So when you hook this up, you're actually going to be hooking up your meter the same way you would to measure voltage. So I have my negative lead in common, positive lead in my voltage jack, and I have my meter turned to DC volts. All right, so that's what we do first. Now right now, it's actually giving us a nice 0 reading. But in case you don't have a 0 reading on here, you first need to press the 0 button. All All right. Now I like to use this scale. You have multiple scales, but this one is probably the easiest to use. And this is 1 millivolt equals 10 milliamps. So if this meter is going to show, let's say 1 millivolt on it, which would be 0.001 right here, then that actually means that it is 0.010 or 0.010 amps. Okay, so we're just moving that decimal one place over. It's all that it is. Okay, so try not to get too confused about that. We will go over that in another class. Okay, so right now I have my low beam headlight on, and all I have to do is clamp this around the wire that I want to measure amperage on. So in this case, we know from looking at the wiring diagram that our beige with a white wire is our power feed wire to the low beam filament. So we can just hook this on. Okay, and magically it gives us a reading. So this is fantastic. We have a amperage reading, or, well, if you want to be technical, which, well, we do want to be technical. We have 440 millivolts, or 0.44 volts, which if you translate it into amps is 4 amps. Okay, so let's try not to make this too complicated. Take that decimal place, move it over 1, and instead of the V, flip it over. You've got an A for amperage, and you have 4 amps. Now, before we move on to check how much amperage the high beam circuit is using, we're going to check to see how much amp or how many electrons are flowing out of the bulb. Should be the same or very close to the amount of amps and the amount of electrons that were going into the bulb. We don't ever lose electrons. We can lose voltage, we can lose that pressure, but we will not lose our electrons. Okay, so now my high beam headlight is on, and now we're going to measure the amperage of the high beam circuit. Now take a moment to think about it. High beam circuit has less resistance, so we should have a little bit more amperage flowing through the high beams. Let's see if that's actually true in real life. Okay, so I got my inductive pickup hooked up, and look at that, we do have a little bit more amperage. Okay, we have, instead of 4.4 amps, we have 5.1 amps. And that's enough of a difference to make a big difference in the brightness of our headlight bulb. So when we are creating circuits and we're troubleshooting, we have to understand that even 0.6 of an amp could really make a huge difference in how our circuit is functioning and operating properly. Okay? Now again, just like with the low beam circuit, all right, we can measure how much amperage is coming out, and it's about the same. Now you might notice, okay, we have a power feed for the high beam filament and we have a power feed for the low beam filament, but why is there only one ground? Well, this circuit can share a ground, and actually all grounds ultimately are shared. So we have a power wire for each individual filament, and they share one ground. But as long as both circuits are not activated at the same time, we're okay. We're not going to have the high beam and the low beam activated at the same time. And we can see that with our amp clamp as we measure the tan and white wire. There's no amperage flowing through it, so our low beam circuit is not on. Okay, so in conclusion, hopefully everyone understands the relationship between amperage and resistance. We learned and we figured out that a high beam filament, it will use less resistance to allow more electrons to flow, and when more electrons are flowing, the higher the amps, the more power you have, and the more power you have, the brighter your bulb. Now, of course, with our low beam, we don't want to be shining a super bright light in everyone's face, so we need a little bit less light than a high beam bulb or high beam filament, but it still needs to be bright enough so that we can see. Okay. Now there are some bulbs out there that are even dimmer, such as our cornering lights and turn signals. We don't need a lot of power, so we don't need a lot of amperage, so we can have more resistance in our filament. So a good example of that is our nice little peanut bulb. Okay, this is about the smallest bulb you can get, and judging by this bulb, yeah, it's not going to be very bright. And if it's not very bright, we know it's going to have a lot of resistance because we're not going to be able to flow a whole lot of electrons through it. Okay, so we can go ahead and measure the bulb on one side and the other. Of course, we're measuring resistance, so the circuit is disconnected, and we get a reading of 4.7 ohms. And it's not even hot because it's not lit up yet. So we know that once we plug this in, our resistance is going to be even higher and our amperage in the circuit is going to be even less than what we would expect if we just measured it cold. Okay, so we're finally done with volts. We've covered voltage drop, we've covered amperage, and we've covered resistance. So now everyone has a good foundation that we can start working off of. We can actually start testing in the lab and start creating some bugs for Mr. Packer's class. So that should be a lot of fun. See you in class.